Hello and welcome to the third lecture on the Advanced Data Analysis course. This is also the first lecture on the data science part. I'm Ludwig. I'm going to lecture these parts on data science, and these will be online classes. So I'm going to start by talking a bit about how these online classes will run. Then we'll start with an introduction to NumPy. This is the numerical library in Python. We're going to look at simple operations with matrices and univariate data. That is data that is just one feature. We're going to use a continuous feature in a series of examples of points. Then we're going to also look at how to make some simple plots to look at our data. So basic introduction to Pyplot, which is the plotting library we're going to use, and do some simple exercises, finding outliers and taking some statistics from our data and so on. So this will just be a starting session to allow you to get up to speed on the basics of Python that you need, and introduce some basic operations and concepts. So do not see these examples that I'm going to give you as actually practical recipes for data analysis. We will look at more powerful and more practical tools later on in the course, but we will start just by understanding some basic ideas here and understanding the basic elements of the tools that we're going to use. So these online classes will be broken down into two parts. The lectures, which are meant to explain the theory and do a brief introduction to the exercises, will be recorded a few days before each session. The link to the video will be available on Moodle, and you should watch the lecture before the scheduled session. And then the tutorials will be mostly to help you with the exercise, to discuss the subject matter, and to answer any questions that you may have. So ideally, you should not only watch the lecture, but also try to work on the exercises before the session, so that your questions are more concrete, are more specific about the difficulties that you might have had, and not just some vague questions because you did not start yet the exercise. To do this, you should also download the lecture notes that I will be providing for these lectures. They will also be in Moodle, and they include not only a summary of what I'm speaking in the lecture, but also the exercises for the tutorials. To set up the system, Professor Nuno already explained that you should install Docker and the image he provided. This will include everything you need for this course. So it may be necessary to update the image during the semester if we forgot something, but once you have this set up, it will always work the same way. However, if you did not have time to install it yet, and you cannot install it before next Thursday, so the first session on data science where we're going to do some exercises, you can use a backup plan by using Google Colab. So in this case, you don't need to install anything, you just need a Gmail account, and you can use that for the first exercises. In any case, for the exercises, you're going to need to use data files, so you need to place them in ideally in the working folder with your notebooks. This will be the simplest solution. So make sure that you understand when you install Docker and the Docker image, where is the folder that you are mapping to your Docker image, and place the data files there. If you're using Colab just to get by this first week before you install everything, then you need to map your Google Drive in Colab so that you can access the files. Note that this slide is only relevant if you did not install the Docker image yet. So if you install the Docker image, there's no need to worry about Colab, because this is just a backup plan if you did not have time to install it. So if you need to use Colab for these first exercises, go to the Colab page here. You need to log in with your Gmail account, and then you have a Jupyter notebook. You can start in the first cell by just copying and pasting this code. This code will map your Google Drive to this Drive subfolder of the content folder in Colab. When you run this, you're going to see a message like this, and it will ask you to go to a link, follow a link, and retrieve an authorization code. That link will ask you to log into your account, and so you grant access to Colab. You grant Colab access to your Google Drive. Afterwards, you can change to the folder where you're going to keep your data. For example, if you follow this recipe and you create ADA-Data folder with this name in the root of your Google Drive to store your data files, then this would be the command to change to that folder. And from here on, if you put the data files into this particular folder, then you can access them easily from your notebook just using the file name. But note that this is only if you did not install the Docker image. So if you have everything running on the Docker image, don't worry about Colab. Okay, so now let's move on to the actual subject matter, and we're going to use this Python library for handling numerical data, Numpy, because this makes it a lot easier to work with the data and load the data and manipulate the values and so on. So we have this file, heights.txt. I will provide them also in Moodle for you. And this is taken from a data set. I have the reference in the lecture notes that this data set was studying height and weight perceptions among people in gyms, if I remember correctly. And it was a questionnaire for 200 men and women who participated in this study. But I just took the height data. So this is a feature extracted from that data set. The second column has the height of each participant in centimeters, and the first column indicates the sex. So if it's 0, it's a male participant, 1, a female participant. And this is the actual format of the text file, which makes it easy to load using NumPy. You start by importing the NumPy library. So this command tells Python to import a NumPy library and give it this alias np to make it easier to use objects in the library. And then we have here, we're going to store in this data variable the result of calling this function, load.txt from the NumPy library, to load our data file. And since the file has the correct format, this function will return a NumPy array with the numerical values in the file. So this NumPy array, you can imagine it as something like a list of lists. You should have an idea now what lists are in Python. But it's more powerful than that, because you can actually access rows and columns inside the matrix independently. So you can do something like this from the data object. I want the first 10 rows and all the columns. And this gives us the first 10 rows of our data file. So these are the values in the first 10 lines of the file. This is a total of 200 rows here. Okay, so this is how we load the data into a NumPy matrix, a NumPy two-dimensional array. Now, if we want to extract parts of the matrix, we can do this slicing, which is similar to slicing lists. You specify the first slice point, which by default is the beginning of the array, the last one, which by default is the end, and the step. You can have negative indexes here to count from the end backwards, and then you can extract from the matrix the combination of slices on rows and columns. For example, with this, I'm asking for the first 5 rows and the second column of matrix M. Remember that indexing in Python starts at 0, so index 1 is the second column. This will give me the last 5 rows because I'm counting from the end in this -5 and then all the way to the end of the array, and I'm asking for every other column starting at the beginning and finishing at the end. So basically, this is going to give me the odd columns, the first, the third, and so forth. This will give me the even columns, and so on. So this way you can easily extract information from the matrix if you know what parts of the matrix that you want. And note that these NumPy arrays have an arbitrary number of dimensions. So you can have 3-dimensional, 4-dimensional tensors, and so on. In general, we are going to use 2 dimensions because usually our data is in tables which have 2 dimensions. So now we loaded the data, and one simple way of analyzing the data is just plotting it to see what it looks like. And a simple way to do that is to use the Pyplot module in the matplotlib library. So you can import matplotlib pyplot, and so that we don't have to write all this every time we use anything from Pyplot, we can give it also an alias called plt. So this imports does something similar to what we saw here. Here we imported NumPy with this alias np. Here we imported Pyplot from matplotlib with the alias plt. Now this part is optional, you can omit it. I'm just setting the style to Seaborn because I like the way it looks. I like it better than the default one. If you omit this line, then the plots will look a bit different from the examples I have here, but it's not a problem. And there are several other styles. So if you want, just take a look at the documentation, what styles are available, and choose the one you like best. This is not very important. This is the actual command for plotting our data, here, the third line. So I'm calling the plot function from Pyplot, and I'm asking to plot from my matrix all the rows and the second column. So this will be just this second column here, which contains the height values. And I'm just plotting the height values. And this will be the look of the plot that you get. So you have these lines joining the different points together. Now there are 2 problems here. First, we have this weird point here. I'm going to leave that aside for the moment. We'll solve that problem later. But another problem that we have is that we are looking at these lines, but these lines actually don't mean anything. So each point represents a different person, and the lines are joining the different people together, but they are not supposed to be joined because the order here is random. It doesn't matter who comes first or next. I just have a set of values. So one thing that we should be careful is that sometimes in data analysis we can represent things or show things that actually don't exist in the data. For example, these lines suggest to us that there is some relation, that the height is going up here, then is going down, and so on, where that is actually false. There is no particular ordering of our sample that is significant because they are independent people, so the lines are suggesting something that should not be there. That's easy to fix. We can, when we plot anything with the plot function, we can add a string that specifies the format. We will see more of this later, but for now I'm just putting here this little dot so that instead of joining the points with the line, Pyplot is now just representing each point with a dot. So there is no line here. And this gives us a more accurate or a better representation of the data because it does not suggest that different people are linked together as that line suggested. Now we have this problem here, which apparently there is someone who is 57 centimeters tall. This is a bit strange, and it's clearly an outlier. And now the question is, what do we do with this point here? This is not a trivial question to answer because outliers can be many different things. Can be just mistakes, that value is simply wrong. It can be something that is very rare, but it appeared in our sample by bad luck, by sheer chance. It may be that there are extreme values that are not rare, but we don't really want them because they are not representative of something that we are looking for. Or it may be that they're actually valid data and we need to take them into account. So when you have outliers, you need to try to understand, or at least be explicit about your assumptions when you're deciding how to deal with them. We are not going to focus too much on that because that is very problem dependent. It depends on the actual data we are dealing with. But in this case, we will assume that this was a mistake. So it seems more likely that someone, for example, forgot to type in the 1 on the 157 rather than just being a person that was actually 57 centimeters high. So this is what we're going to assume. We're going to assume that something that deviates too much from the norm here, we will assume that it was some recording error, and we will remove those outliers. So let's generalize this and think about how we can do this in general, not just remove this one individual point manually, but create a procedure, a process of cleaning our data where we specify how to remove these outliers. So let's say we compute the mean for our data, and we remove everything that is more than some number of standard deviations from the mean. So we are implicitly assuming this is approximately a normal distribution, and if someone is too far, if some point is too far from the mean measured by in the standard deviations, then we take it out. So this is basically when we are dealing with the population, this will be the z-score, and if the z-score is greater than some threshold, we remove that point. So let's create a function for this. We're going to generalize this and create a function to help us do this with our data. The function will receive as input an array of values and a threshold, a limit for the z-score, and then it will return a Boolean mask of true and false that marks with true each point that is an outlier. I'm going to explain this a bit more, but first I'd like to address this part because usually when you use Jupyter, it's very convenient to just copy paste code from one cell to the other or do things like that, but that is not very good in the long run for programming, and functions are a much better solution to this problem when you have to reuse code. So a Python function is an executable object that specifies a recipe that you can then apply each time you execute that object. So if we are going to clean outliers from our data following more or less this recipe regularly, it's useful to have this function and then just call the function every time we need it. So this makes the code a lot more structured and easy to write complex code by joining together simpler elements. So let's first look at this idea of using Boolean masks. So we want to go through our data and mark everything that is an outlier. We can easily do that with NumPy because we can compare a set of values to some particular value. And what NumPy does is produce an array that contains Boolean values that are the result of the comparison of each element in this array with the value that we are comparing to. So in this case, this is a greater than 2. The first element of a is 1, and 1 is not greater than 2. So the first element on the result is false. The same for 2. 2 is not greater than 2, so this is false. But 3 and 4 are greater than 2, so these two are true. So we can create an array of Boolean values by comparing each element of our array of data to some threshold. We can also use these arrays of Boolean values to index specific elements in our array. So for example, if I want from the array A everything that is greater than 2, I can say that I want from A those values that are greater than 2. This expression here will produce this Boolean array, and when I insert a Boolean array as an index for a NumPy array, it will give me only the elements corresponding to true values here. So this makes it easy to extract values from a NumPy array based on some condition that we want to impose. We also need statistics. We need the mean and the standard deviation in order to apply our recipe of discarding points that are more than some number of standard deviations away from the mean. This is also easy to do because NumPy has all these basic statistics function, the mean, the standard deviation, the median, the max, the minimum, and so on. So as you can see, all you need to do is call the NumPy function. So I'm specifying that the function is inside the NumPy library, and I provide the array that I want. For example, in this case, I want the average, the mean of the height. So I'm giving to this function an argument which is all the rows in my data matrix, but only the second column. So I'm omitting the zeros and ones that mark the sex of each participant. So this will compute the mean of the height, and it will give me the value, the standard deviation, the median, and so on. Okay, so now we're ready to write our function. We define functions in Python with this keyword, def, for defining functions. This is the name of the function, return outliers. And inside parentheses, we specify the parameters, which are the local variables that belong to the function that will receive arguments that the function will then use. So these are, let's say, the drawers where you'll put in the values the function needs. Then we have this column. This is these two dots indicate the start of a code block in Python, and then the indentation here indicates to the interpreter that all of this belongs inside the function. So basically the function stores this recipe and it will apply it to whatever values we provide. And what it will do is it will compute the mean value of the series of numbers of values that we give it. It will compute the standard deviation, and this will be in these two local variables, m and std. And now the outliers will be an array of booleans that will be determined by this condition. So first we subtract the mean from each point in our data series. When you do this with a NumPy array, you can do an operation between a NumPy array and a scalar, so a simple number, and it will distribute the operation over all the elements. So if I have 200 values here, I am subtracting m from each of them, and the result will be an array with the results of all those subtractions. Then I use this absolute, this ABS, it's the modules, the absolute value of each of these numbers. So I'm also always taking the positive. And then I'm checking if the result is greater than the product of this z-score provided and the standard deviation. So for every point where the absolute value of the difference between that point and the mean is greater than z-score times the standard deviation, this will be true. Otherwise, it will be false. And this is a generic way of marking the outliers based on this z-score threshold that we specify. So now we return the outliers. So this means that when this function returns, it returns the array of true and false values showing where the outliers are. And this is how we can use the function. So you can use this code in one cell, execute the cell. When you execute the cell, it doesn't seem to do anything, but this object is now present in memory, and you can execute that object. So we can do it like this. The outliers are the result of this should be return outliers if we do it like this. The return outliers function. This is the same name as the function, and we provide as first argument all the rows of the data matrix and the second column, which is the height values, and 3, which means that we consider an outlier any point that is 3 standard deviations away from the mean. And this is now the array of true and false that we have indicating the outliers. So if we want to know what are the outliers from our data, we can say that we want to see from our data the rows corresponding to true values in our outliers variable and the second column for each of that rows. So this returns only one value because we only have that one outliers, 57 centimeters. If you want those results that are not outliers, we can easily negate the outliers using the tilde character there. So if you put a tilde before the outliers, you do the negation, and now you get the ones that are false in the outliers and become true in the negation. Note that the actual name that you use here must be the same as the function. So if I had written this find outliers, then I would have to call the function find outliers. But the name of the function is whatever you want. It should be something that is descriptive of what the function is doing, but you can choose for yourself. So now we can visualize the data without the outlier. We can return the data. For example, we can do this selected, for example, equals data, and the data that has not outliers. So you're only looking at the rows that are not outliers and all the columns, for example. This way we get the complete matrix, both columns, but only the rows that don't have outliers. This is one way you can use the outliers, the result of this find outliers function, to extract only the regular values from your data. Okay, so now looking without the outlier, we can do the plot again, but it's still not very informative. We see a cloud of points. We know that the height is varying more or less between 150 and nearly 2 meters here, but we don't have a very good idea of what the distribution is. One way of doing this, visualizing a bit better the distribution, is by sorting the values that we have. So let's suppose that we kept the selected values in this selected heights variable. So if you want to do this, you can do it like this, and the selected heights is from the original data matrix only the rows that are not outliers. So we now dropped this point. We don't have this point in our data anymore. And this is what we see here. And now we can sort the values from the second column. So we only take the height values. Note here we are taking all the rows from this matrix, but only the second column. We put it in the sort function from NumPy, and it will return the same values but sorted in ascending order. So first the smaller ones and so on. And now we can plot this. We can plot the sorted values, and we can add labels to our chart. So the y value here is the height, because we are plotting the height of each individual, and the x label is the rank of the individual in the sorting. So the first person here is a bit below 150, then the second person, third one, and so on. Looking at this, we have an idea that there are, in the extreme values, the height is changing very rapidly. So there are few people with approximately the same height. But then as you start approximating this mid part here, then it's increasing slowly, which means that there are a lot of people with similar heights around here. And then again, when we reach the extremes, it grows rapidly. So this is a bit like a cumulative distribution plot, but it's a bit strange because it's turned sideways. It shouldn't look like this, the actual cumulative distribution plot. But it's easy to fix. We just do the plot in a slightly different way. So it's the same thing. We are sorting the values, and now we are plotting the sorted values. But instead of just giving the sorted values to the plot function, which makes the plot function by default just put the index of each value on the x-axis, we give two arrays here. First, we give the heights, so that the plot function uses the heights as the x-axis, the first axis. And then for the y-axis, we give a uniformly distributed set of points, so they are evenly distributed between 0 and 1, with the same number of points as the persons that we have. So actually this would be 199, because it was the 200 initially, but we dropped one outlier. But we don't need to count them ourselves. We use this len function. This gives us the length of the array. So this is the length of the sorted heights array. It's the number of elements in the array. And this lean space gives us an evenly distributed, linearly distributed set of points between two values, the lower bound and the upper bound. So this is 199. This will give us 199 points uniformly distributed between 0 and 1. And this is what we put here on the y-axis. So this is a simple way of doing a cumulative distribution plot. Well, not simple in the sense that it's the simplest way to implement it. You could use libraries for that, but to help us understand what we are looking at here. So if you choose some height, for example 170, you can see that about half the people are at most 170 centimeters tall. So half the people are below this height here approximately. If you go more, for example 180, then 80% of the people or a bit more are at most 180 centimeters tall. So this gives us an idea of how the heights are distributed. There are some few people here who are very short, some few people who are very tall, but then most of them seem to be around this part, that mid-range. Now, one question that we may have is, we are looking at this distribution for both sexes, for men and women, so all the data set together. But we may ask if there are some tendential differences between the sexes. So we expect there should be. But to check this, we need to split our data into male and female, into two data sets. This is easy to do. We're going to see how, but if we want to split our data into several subsets and then plot this cumulative distribution plot for each of the subsets, we're going to need to plot this several times. So every time you need to do something several times, it's a good idea to write a function with the recipe for doing that, and then you simply call the function how many times you need. So let's write a function to do this for some generic set of values. Our function called cumulative distribution, for example, cumulDist, will receive a set of values. We'll create a new set with the sorted, with these values sorted in ascending order, and then it will do this plot that we did here. So basically, we use the values, the heights in this case, for the x-axis, and the fraction, the growing fraction, for the indexes of each of the examples in the y-axis. So this is what we're doing here, but in this case we start with some generic set of values, we apply the sort function, and then we do the plot. So now, if we have several sets of values, we can just call this function and do all the plots that we want. For splitting the data, we can resort again to Boolean arrays. So if we have this matrix, which is the original data except apart from the outliers, the one we discarded the outliers from, we can compare the first column, the column of index 0, to 0. So we select all rows, the first column, and we compare this array to 0, and we get this array of Boolean values. So every row that has a 0 in the first column corresponds to a true value here. This is a male participant. If not, then it's a female participant, and it will be false here. And we can use this array to index the rows of this matrix. So to split our data, we can do something like this. The male participants are from our matrix, those in the rows where the first column of our matrix is equal to 0. And we use that Boolean array to pick out just the rows that we want. Since we are already extracting the male participants, we don't actually need this first column anymore, because it will be 0 in all the values. So let's just take the second column for these rows. So we have the height of the male participants. And now we do the same for the female participants, but we just change the condition there. So the male participants are indicated by 0, the female participants by 1. So we just change the comparison there, and we extract the female participants. If we had different categories and set a different number of categories, it would be easy to generalize this and just do this for each category that we had. And now we can call our function, the one that we created here, to plot each of these distributions. So we called the function with the male, the heights of the male participants, and then we call it again with the heights of the female participants. And since we are doing two plots in sequence, we are calling plot 2 times each time we call this function, Pyplot will automatically change the color of the series that is plotting. So this, I have to explain this a bit, because when you run the cell, any plot that is in memory will be captured by Jupyter, and you'll see the image, and then the plot will be discarded in memory. So this means that if I do a plot again in a new cell, it will create a new chart. But if I do several plots in the same cell without explicitly telling Pyplot to create a new chart, then the series will be plotted in the same chart. And this is what's happening here. I have plotted the male heights and then the female heights, and these were plotted like this. First the male heights here in blue, and then when I plotted the female heights, Pyplot changed the color and plotted in green. And since I have several series, it's useful to add a legend. So if you call the legend function, you can provide a list of names for your different series in the same order as you plotted them. So male, female, then I call it male, female, and I have a legend there. So in this case, when we do it like this, we can see that there are differences in the distribution of heights in males and females. Namely, as expected, male participants tend to be taller than female participants. Another way of looking at these distributions is doing histograms. Histograms are easy to do with Pyplot. We just call the hist function. And so we give the male data, the female height data, and it will draw the two histograms in the same chart. We can add the legend, but this is a bit not ideal, because the distributions have some superposition. There are some women who are taller than some men, so their heights cross somewhere around this region. We can see this superposition if we add transparency. So there is in the plot instructions, you have usually this additional argument, which is alpha, which is the opacity of the representations, the drawings that Pyplot is doing. So if alpha is 1, they are fully opaque. If alpha is 0, they are invisible. But if you use an intermediate value, for example 0.5, then they'll become semi-transparent. And now we can see each of the distributions and where they overlap. You can also change the colors if you want. So you can say, for example, male with the color B, this is for blue, and female with the color R, red. And now you have different colors here. You can specify the colors in many different ways with the RGB codes and so on. There are many different names also for specific colors. You can see then in the documentation. But this is just to give you an idea that you can customize the plots a lot. But in this case, the main part was basically to solve this problem of the overlap of the histogram, so that we can see both distributions even where they overlap. Okay, so now I'll just give a brief rundown of the exercises that you should do this week corresponding to this lecture. So in the lecture notes, where you start on the exercises will depend a bit on how confident you are on your proficiency with Python. So if these things like using variables, functions, operations, and so on are still a bit confusing, I would advise you to review your Python introductory course before starting to do these exercises. Because even though I'm explaining things step by step, I am assuming that you have at least the first introduction to Python, and you can already start doing some basic programs already. If this part is not really what is troubling you, but you still are just a beginner and having sometimes following these explanations, then I would advise you to follow the slides and lecture notes and implement these things yourself. So actually run through this code, write this code in the notebook, try to figure out what parts are missing, because sometimes I skip one step or other, but they should be fairly obvious, and you can follow the lecture notes where these things are explained in more detail. So basically look at this lecture as a tutorial that you can follow to go through this first part. Then the first exercise on section 1.2.1 is for those who are not familiar with NumPy. So you already know a bit about Python but never used the NumPy library, and these are just a few simple exercises for handling a NumPy matrix, where you select rows and columns and change the matrix and so forth. If you are familiar with this, then you can just skip this part and move on to the exercises, which are just two simple exercises. The first one is to count the values in an interval. So for example, suppose we want to know how many men in this sample are between 170 and 180 centimeters tall. We generalize this, so we write a function that allows us to ask this question in general, given a set of values and a lower and upper bounds, how many are inside that range. And for this, you're going to use the sum function in NumPy. This is useful, has one very useful characteristic for this kind of problems, because when you sum a Boolean array, false values count as 0 and true values count as 1. So sum allows you to count how many true values you have in a Boolean array. And the logical AND function in NumPy allows you to do the element-wise conjunction of two Boolean arrays. So if you have two arrays of true and false, you put them in logical AND, and you get an array of the same size, where each element is the value on the first array and the value on the second one. So this will allow you to do the comparisons with the lower and upper bounds, do the conjunction of those Boolean values, and then figure out how many true values are there. The other exercise is a bit more complex. It allows you to ask questions like, what is the fraction of men that are taller than 90% of the women in the sample, for example? So this function will receive both arrays of heights, one where you're putting the question and the reference one, and also a percentile that you want to use as reference. So you would give the heights of men, the heights of women, and 0.9, and it will figure out the fraction of men that are taller than the 90% percentile of the women heights. For this, you need to sort the array. I've given you examples of that here. You need to use round, because to get the percentile, you need to convert, or to get this, you need to, after sorting the array, convert this fraction into an index, and the index must be an integer. So you need to use round from Python. Do not use round from NumPy, because round from NumPy rounds the value but keeps it as a float, not as an integer. And then you can use len again for computing the length of the array and so on. These are simple functions, and you have the answers at the end of the chapter. But I would ask you to try to think about them before looking at the answers, and even if they don't work, try to get them as close as possible to working, so that you have some specific questions to ask me on Thursday about the difficulties on these exercises. Okay, so to sum up this introduction to NumPy and Pyplot, we saw how to load data and to manipulate these ND array objects, these matrices in NumPy, and how to visualize the data. We also saw these basic concepts, statistics, outliers, and so on, and these cumulative distributions. But the idea here was to start introducing this way of thinking about the data and about how we are looking at the data. So be careful about things like using representations that show things that don't actually exist. Try to be explicit and as rigorous as possible when you specify how you're processing the data. For example, it's tempting when you have an outlier like that 57 centimeter height just to go into the file and delete it. But that is not a reproducible and explicit operation. It's much better if you generalize and you say, I'm removing everything that is 3 standard deviations away from the mean, and then you write the function for that and you apply the function, because then you have an explicit notion of what you're doing to your data. And also this idea of using cumulative distributions to get a feeling for how the data is distributed, the histograms, and so on. Now I recommend that you read, or at least take a look at the lecture notes. I will put them in Moodle 2 along with this video. So chapter 1 corresponds to this first lecture, and at the end of that chapter you have the exercises. You should also read the textbook on chapter 2. Sections 2.1 and 2.2 cover approximately what we saw here. It's handled a bit differently, but it's good to read things from different perspectives. It helps understanding. The documentation for Numpy and Pyplot, it's not so much for you to read, because this is very boring to read in one go, but you should take a look and browse a bit so that you have a notion of where to find the details if you get lost and you need to look up how to do things. So that's it for now. Hope to see you next Thursday. Bye.